Hello, my dear lovely NEET Lions. Welcome aboard. Hello, Madhumati Krishna, Harbourine, Philo, Hema, Satyashri. Welcome, Sneha. Welcome, Hema. Welcome, Chitra. Welcome, Shalini. Hello, Atluru. Welcome, Krishna. All my warrior Pandus waiting eagerly for the work power energy class. So, guys, this chapter plays a very crucial role in many other chapters like electrostatics, even magnetism, even rotational mechanics, even sometimes circular motion. You will see so many concepts from this chapter are directly picked up in so many chapters of 11th and 12th. So pay close attention to this chapter. It's very laddu type of thing, but it will give you marks and you have to be attentive. So all the three concepts, work, power and energy, in today's class, where we'll start from basics and scale you up with the applications, with the help of all the concepts, be it in NCERT, be it your PYQs, and right from the scratch we go up in the RNA series. And there will be lots of problem solving sessions ahead. So make sure you are subscribed on the channel and you have marked your attendance, my dear lovely warriors. Hi Soni, hello Sushmita, hello Santosh, hello Dikshi, Shruti Blessy, hello Sudarshan. Nice to see all of you guys. And I know you guys were eagerly waiting for this class. And unfortunately, I was not able to take the classes last week. So here we are trying to cover it up. And obviously in full speed now, because right now we are nearing towards the end of September slowly. And guys, there is no time to waste, because remember, we have to complete as much as possible in the next couple of months and then start with the revision mock test. I know you guys are eagerly waiting for it because everybody wants to complete the syllabus and start the mock test. That energy is only very different when we start with the revision. But for that, you need to make yourself a promise that you are watching these classes regularly, which are being made for you with great effort. Okay. So thank you for liking and stay subscribed on the Vedantu NEET English channel. So let's begin with the class. Thank you for liking, guys. Thank you. Hi Adluru, Krishna Warrior Pandu is here. Javita, hi. Hi Sneha, thank you for the fire. Madhuvati, thank you so much, guys. Thank you. All right. So let's start with the concept of work. Then slowly we'll go to kinetic energy, then potential energy, mechanical energy, conservation, and at the end it will be power. Okay. So that is the basic flow of this particular class. So guys, remember, you say that work is done in physics. You say work is done in physics when some kind of force pushes it and you see some displacement. That is what you might have learnt in 9th standard. So let me put a very simple perspective to it. Just imagine guys, there is a bank, okay, and then there are people who have accounts in the bank. Maybe there is a beautiful Champa who has an account in the bank, and then there is also a Pandu who has an account in the bank, and this Pandu has some money stored in the bank. This is the stack of money. Pandu has little money, maybe Champa has even more money. So you can see Champa has even more amount in her bank, and maybe Champa uses a phone or a QR code scanner shown by Pandu, okay, to do some UPI transaction. Okay, this is Champa's phone and Pandu is showing QR code. Champa scans that QR code and she can basically transfer money to Pandu. She's transferring money to Pandu. Maybe because, I don't know, maybe Pandu did some work, maybe Champa owed some money to him, or maybe Pandu's birthday is there, Champa is transferring money to him. I don't know whether your friends transfer you money or give you some gifts during birthdays or some special events. If they do, they are your very good friends. Keep them together. Just kidding, guys, not for the money. Friendship should always be because of the values, because of the help that they give you. Anyways, so Champa is basically transferring some money to Pandu's account, and Champa is using her phone, maybe Google Pay, something like that. Now in this process, imagine if there is only one bank in this whole world, Champa's account might have some little lower balance after this transaction. Pandu might have a slightly more amount in his account, but the bank will not lose nor gain anything. Let's neglect income tax, taxes, etc. So the bank as a whole, so the bank which is there, which is helping with this particular transaction, that will neither lose nor will it gain. Do you guys agree with it? Gopika ma'am is there. Oh, Champa is rich. Yes, Gopika ma'am, Champa is very rich. When will we become very rich, Gopika ma'am? But you know what? We are very rich actually. We are having the love and the likes and the support of lakh plus students across the country. And that is probably the biggest richness that we have. Thank you for all the love, guys. Thank you for all the love. You can't buy these things, you can't buy these comments, you can't buy these likes, you can't buy this watching. And the best part is students love us because we do so much for all of you. And honestly, that is what I feel is important, right? Okay, guys. So in this process, like we saw that the bank neither lost nor it gained. Let me tell you, what if I told you the bank is just like the universe? This Pandu Champa are just like your systems. This money in the account, the money in the account is just like your energy. And this process of transferring money from one system to the other system, this process, what if I call that process as work? And the method, the agent which is used, like in this case, UPI transaction, maybe you give it by cash, maybe you do account transfer, maybe you withdraw the money and then do it, whatever. So guys, what if I told you that agent which was involved, in this case the UPI transaction, is basically the force. So this is the entire chapter just in just probably 1 or 2 minutes. Yes, just think about it. Whenever somebody does work, the energy goes from one system to the other system. And for doing that, you need force. Without force, you cannot do any kind of energy transfer. For example, I take a ball and I throw it towards you. I have applied a force. My energy went inside the ball as kinetic energy. The water which is falling from the top falls on a rotating turbine. The potential energy was converted into some other energy, and it happened because of the gravitational force. So force is needed. Without that, the energy can't flow from one system to the other. Every system has an account balance, which is called as the energy, which is how much capacity do you have to perform work. How much capacity you have to perform work, and work is the process of this energy transfer. And whenever this process happens, whenever one system loses energy, the other system gains energy. When this gains energy, the other loses energy. The total bank balance always remains constant in this universe. Is this absolutely clear? Everybody with me on this? Understood? This is the whole chapter's summary. So let's start with the definition of work now. So work guys. So work is nothing but is the process. It's the process of energy transfer. It's the process of energy transfer via an agent. And what is that agent? The agent is called as force. If you ask me about energy, what energy is, it is nothing but is the capacity of doing work. It is the capacity of doing work. It is the capacity of doing work. And I can also mention this, that the total energy in the universe, total energy in the universe is always going to be constant, is always going to be a big fat constant. That is what you should know. Correct. So these are the basic ways in which you can define these things. But the formal way, or rather the formula way of defining work, that is what we are going to start off with. Now see guys, work happens when you not only have the agent, which is the force, but also there should be displacement. For example, I have this chair over here. I don't know whether you can see it. So this chair is there, guys. Yes, I am doing some work. I applied some force, and I lifted this chair. Oh my God, yes. So I did some work. Force and displacement were there. I am applying the force, but the chair is not moving. I am applying a force on a big rock. That rock doesn't move. Then work is not said to be done. You might be wondering, sir, you are pushing that rock, sir, you are pushing that chair, but you are getting tired. How come you say you are not doing work? I would say I am working. Sir, even I tell my parents and my teachers when I am sleeping in the house, I was working, ma'am, I was working. I did not get the answer, ma'am. That's why I did not complete the homework, ma'am. Sorry, ma'am. Sorry, ma'am. So, sir, even in such situations, I tell my teachers that I was working when I am sleeping. And you are saying you are pushing a wall and you are so humble to tell that you are not working, but you are getting tired, sir. How can you say that? So the answer for that is, see, I did not do work on the wall or on the rock or on the chair. Rather, my cells within the body did work within themselves, increased metabolic activity, increased respiration, increased body activity, muscular energy, which was gone in sweat and all the bodily processes, which probably had an increased rate. Maybe my heartbeat increased, maybe my respiration increased. So it went within myself. It did not go into the chair or that rock or the wall. So I did not do any work on the wall. Rather, the body cells have done work on themselves, and that's how the energy was lost, and that's why I felt tired. Hi Maroli, hi Arpana. Is that clear, my dear warriors? Understood? Hi Sudhakaran. Is that absolutely clear? What is the meaning of work and why you need both force as well as displacement? So sometimes you might be like, sir, I applied force, there was displacement, but is it possible that there was no work done? Yes, it is possible. Just imagine you take a thread and you attach it to a stone and move it around like this. You move it around like this. The thread applies a force, the thread applies a tension force, but it never does work on that rotating stone. Reason is that force of tension is perpendicular to the displacement. So as you rotate, the tension force is perpendicular to the displacement, and it never does work because this tension is not what is increasing the speed, not what is decreasing the speed, is not what is transferring the energy. Rather, it is just changing the direction of the motion. Rather, you are doing work by accelerating it, by rotating it, etc. So you were doing work, the tension did not do any work because that force was perpendicular. Keep that in mind. So my dear students, always remember that just because you see a force and displacement, don't immediately conclude, yes, there is work. It might not be in the direction of the displacement. It might be completely perpendicular. In such a case, it only can change the direction but not change the speeds. It can't do any work. For example, I am carrying something, maybe this particular book over here. I'm carrying this particular book on my head. I'm moving like this. Tell me, isn't there a normal force on this book? Isn't there a normal force on this book? Is the normal force doing work? No, right? Why? Because I'm just moving like this and just moving like this. The displacement is horizontal. The normal force is perpendicular. How can it do work? It's not moving the book up and down. I'm moving the book sideways, horizontally. So normal force did not do any work in this scenario. Keep that in mind. Yep, great. So we will define work as, formally as, force in the direction of the displacement, in the direction of the displacement, in the direction of that particular displacement, multiplied by multiplied by the displacement itself, multiplied by the displacement itself, displacement of that force, multiplied by the displacement of that particular force. So for example, imagine there is a body, maybe it moves some amount and maybe it moves over here, something like this. And in this particular scenario, let's say this is that displacement, this is that displacement. Maybe the force was acting at an angle, the force can definitely act at some angle. And let's say the angle made over here was theta. Then the force will have two components. One is this component, which is perpendicular to the displacement. You can see this component is useless. This is the perpendicular component. This is the component which is along the displacement, which will be f cos theta, which is basically going to be parallel to the displacement. This is the component which does work, this doesn't do work. So this doesn't work. This doesn't work, rather this does work. This does work. Keep that in mind. So as per this definition, the force along the displacement will be nothing but f cos of theta, and the displacement itself will be nothing but s. So that is basically your work. Symbol for work is W. So f cos theta into s. F is the force, theta is the angle between the force and the displacement, s is how much you have moved. Correct. Now, okay. Now the next thing is force is a vector, even displacement is a vector, and I'm seeing the magnitudes getting multiplied along with the cosine of the angle between them, which means that I should use the definition of dot product. If you remember dot product, exactly the dot product of two vectors A and B is A into B into cosine of the angle between those two vectors, A and B being their magnitudes. So hence I can say, I can just put this as F vector. I can just put F vector. I can also put S vector. That's it. And that will be work is F dot producted with S. This is also perfectly fine. Nothing wrong in this definition. Keep that in mind. Okay. It's one and the same thing. So let me just block this off for all of you. Yeah. Work is F cos theta into S or F dot of S. Now, if you ask me about the units of work, and other things, first of all, work is a scalar quantity. There is no point in mentioning I did 100 joules of work in north direction. If you say that, you will get one tight slap. Why did you tell me the direction? Did I ask you? No, sir. But I thought I will just tell I did work in north, sir. No need. It's just like asking, sir, my bike, no sir, it has a top speed of 200 kilometers per hour. Very good. In east direction, one tight slap you will get. What do you mean by in 200 kilometers per hour top speed in east direction? In west direction, 200 kilometers per hour is not the top speed. So, understand, speed is a scalar quantity because direction is irrelevant. Now, I ate something. I got 500 units of energy. Whether it is in north or in south, how does it matter? Which way I am looking? How did the food go? It doesn't matter. I pushed something. I spent some energy. I did some work. Doesn't matter whether it is north, east, up, down. Doesn't matter. So work is a scalar quantity. It does not even follow the rules of vector addition or subtraction. Okay, so it's a scalar quantity. Direction not important, not needed. Okay. Unit wise, yes. We define 1 joule of work as 1 Newton force displacing it by 1 meter. 1 Newton force displacing it by 1 meter. This is the SI unit. The CGS unit is erg. 1 erg is when 1 Dian of force is displacing it by 1 centimeter. There is a conversion factor between the two, and that is 1 joule is basically 10 to the power 7 ergs. 10 to the power 7 ergs. That is the conversion factor between CGS and SI unit. Now, one more thing which you should also know over here is that just like this body which was there, just one second. This was the displacement. This was the displacement. This was the force. We can say that, listen, work is force dot displacement in vector form. But we can also say that work is F cos theta. Now F cos theta over here represents this F cos theta, which is force along displacement, force along that particular displacement into the displacement itself. But there is one more way of writing work, and that is you just write it as F into, imagine, instead of putting cos theta here, put cos theta there, it will become Fs cos theta. Which means you take the displacement's component and you take this displacement, which is then S cos theta, which is the displacement along the force, displacement along the force. This is also fine, not just force along the displacement into displacement, but also force into displacement along the force. This also works, it's one and the same thing. Okay, so along the displacement, instead of that, you can also say displacement along the force. It's one and the same thing. Is this absolutely clear, my dear warriors? Adluru, I'm very good. Hi, Prasad. Krishna, I'm very good. Thank you so much. Thank you, Sumi. Much better. And yes, I'm all fine. And we had a great celebration in Pune, in the offline center. I was there actually for the 𝐂𝐤 𝐎𝐥𝐚𝐲𝐥𝐢𝐬𝐭, and at my home, by the way. Yeah, so we had a really, really great time and met a lot of students. In fact, around 500 to 700 students here and there. So they all had fun. Yep. Hopefully I'll be in your city very soon. Hi Shruti, welcome. Clear? Okay. Great. Now let's do some basic questions on this before we go ahead. Okay. Say for example, I tell you, the force acting is 3i cap minus 2j cap, and the displacement is 2i cap plus j cap minus 3k cap meters. This is Newton. What is the work done? Come on, guys. Let's see if you guys can do this question. It's not that difficult. You have to find the work done. Force is given, displacement is given. So guys, remember, you have to use this definition. Work is dot product of force and displacement, and you know how dot product works. How does dot product work? Come on, guys. So the dot product of 3i cap minus 2j cap with 2i cap plus j cap minus 3k cap. So always I multiplies with I. Remember this. I will multiply with I. J will multiply with j. If there is nobody with k, their loss, nothing will be there. Okay. So 3i into 2i. 3 2s are 6. That's it. Minus 2 into plus 1 is basically minus 2. Nothing for k, so put 0. So answer will be basically 4 joules. Just check this out. Very good, Vaishali. Very good, Shalini. Very quick. Yes, Arpana, I'll be finishing the chapter in this because these are long marathons. Yep. From the basics till your NEET level. Correct. Next, guys. Imagine this question. They tell you that, listen, there is a force of 20 Newton that does a work of minus 10 joules displacing a body, okay, acting at 120 degrees with the displacement. Find the displacement. Find the displacement. That is the question. Okay, let's see how do we do this question. Here the work done is negative. We'll come to the significance of negative in a bit, but let's go purely mathematically. Guys, think about it. Work is nothing but Fs cos theta. Why am I not using dot product? Because I don't think I need unit vector notation here. Everything's magnitudes are given, so it's better to put Fs cos theta because even angle is given. In the previous question, angle was not given, that's why I did not use Fs cos theta. So work over here is negative 10. Force over here is given to be 20 Newton. Displacement, I do not know. Cos theta is nothing but cos of 120 degrees. Now, this 0 will cancel, so it will become minus 1 is 2 multiplied by s multiplied by, what is cos of 120? It is negative half. Cos of 120 is negative half. So 2 cancels, negative cancels. So 1 will be equal to s, or displacement is basically 1 meter. That is the answer. So the body has moved exactly 1 meter forward. Awesome. Now, what is this concept of positive and negative work? You might be wondering. And can the work done be 0? So let me tell you guys. See, I will say that the work done is positive. Work done is positive in either of these scenarios. Like for example, this is the displacement. This is the displacement. And our force is either parallel. Our force is either parallel to the displacement or making an acute angle. Making an acute angle with the displacement. So what happens when the angle is acute? Theta is acute. Theta is acute or basically 0. The value of cos theta will be a positive number. Cos 0 is 1, cos 30, cos 60, cos 89, cos 80, cos 75, cos 28, cos 17. All these numbers will be positive numbers. So because of which the work done will be positive. Example of this would be, imagine you are lifting a box. When you are lifting that box, what is happening? The displacement is in this direction, and even the force with which you are pulling up that box or lifting that box is also in the same direction. So 100% it is positive work. Another example of positive work is, imagine a ball. This is a ball which is falling down. The ball which is falling down. So when it falls down, the displacement is below. The gravitational force, the force of gravity is in the same direction. So it is doing positive work. So whenever positive work is done, you will see that the body tries to supply the energy. It is like a giver, like a donator. Like, you do charity and you are donating something. You give some 10 rupees to some person. You are doing some charity, right? So whenever force does positive work, it is doing charity, it is doing a good deed, and it gives energy to the system. Similarly, you will have negative work. Example for this will be where, say for example, this is our displacement. Either our force is exactly opposite or it is making an obtuse angle. So theta is obtuse or 180 degrees. So what happens in such a case? Cos theta will be negative. Cos 120, cos 150, cos 91 degrees, cos 179 degrees, cos 180 is minus 1. So guys, you will see the cosine values are negative. Remember, all silver tea cups, that trick which you have learned in trigonometry, ASTC rule. First quadrant, everything is positive. Second quadrant, sine, all silver, S for sine is positive. So cos, tan are negative. So that's why you will see cos value will be negative. Many examples are there of this. Imagine there is a ball which is thrown up. So the displacement is on the vertically upward direction, but the gravitational force is downward. So force and displacement are opposite. So 100% it is doing negative work. Even more examples are there. Like for example, there is a box and it is moving and maybe the surface below is rough. So the frictional force will do negative work against the block as it stops. You are going somewhere, it is sucking away the energy. So negative work is not a giver, rather an acceptor, rather it takes energy, it sucks away energy from the system. That's what it is. Yes. Then what about zero work? What about zero work? Now for zero work, there are many cases. For zero work, there are many possibilities. The first possibility is where your force is there, displacement is also there, but they are perpendicular to each other. This is first possibility. The second possibility is that the force itself is not there. The third possibility is that there is force but displacement is not there. Under any of these three circumstances, the work done will be zero. How this? Because you can clearly guess cos of 90 degrees is nothing but a big fat zero. I can give you many examples of this. Even say, example of this will be, let's say this is the moon. Let's say this is the moon. The moon goes around the earth like this. This is the earth. This is the earth. The displacement is here. The gravitational pull is like this. The gravitational pull is perpendicular to the displacement at every instant. Gravity pulls the moon towards the earth. The displacement is like this. It is not doing work. How can earth give energy to the moon? If it gave, then the moon should start rotating fast, tuck, 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 and it will fly off. Nor is it taking energy from the moon. So guys, gravity is not doing work in this case because the force is perpendicular to it. Okay. Example where you have not applied only any force will be, imagine something which is just moving and there is no force only. So velocity is, imagine, constant. There is no force. There is displacement. Displacement is there, but force is absent. So if force is only not there, how can work be done? And the last possibility is where there is no displacement, but you have applied force. Like, say for example, like the same thing which I told you before. There is a person who is pushing a wall. Person pushing a wall. Person pushing this wall. You are pushing this wall. There is no displacement, but force is there. But force is there. Okay? But there is no displacement. Or in all these cases, work done will be zero. So, did you understand the sign convention of work? When is work positive? When it is acute or same direction? When is work negative? When it is opposite direction or obtuse angle? And lastly, zero work when it is either perpendicular or no force or no displacement. In all the three cases, you will see the work done is zero. Now, you tell me in the following cases whether the work done is positive or negative by any of these things. A person pulling a spring, whether the work done is positive or negative. Just think about it and answer it. Next, okay. A string pulling a bucket of water. Next, normal force on a person inside a lift going down. Okay, what do you think is the sign of their respective work by those forces? Okay, come on my dear students. The first one, very straightforward. Person pulling a spring. So think about it. When the spring was being pulled like this, this is how the displacement was. This is how the pull was. You're pulling it. Force and displacement are in the same direction. So what do you think? Yes, the work done is positive in this case. Work done is positive by the person. But if you ask me, what is the work done by the spring? Then the answer will be negative. Why? The spring will try to pull it back. There will be restoring force. There will be restoring force by the spring. It will try to pull it back. Yep. So therefore, work done will be negative by the spring. Keep this in mind. Whenever work is done, right, there is always somebody who is doing positive work and somebody who is doing negative work. It is logical. How is it possible that I am giving money but nobody is taking it? Or if somebody is taking money, somebody must be giving it by force or by not force, that is secondary, but 100%. So guys, whenever there is a taker, there is a giver. Whenever there is a giver, there will be a taker. Otherwise, the transaction only won't happen. Keep that in mind. So, person is doing positive work, whereas the spring is sucking away the energy from that person. Similarly, the string pulling a bucket of water up. So, imagine this is that bucket of water and the string is pulling it up. So, that means the displacement is up and the string is obviously going to apply some kind of tension force. So yes, it is doing kind of a positive work. It is a positive work because force and displacement are in the same direction. Yes, Polari, Pujita, this is full lesson, correct. Next, a normal force on a person inside a lift going down. Now this is a tricky one. See, imagine this is our lift. Okay, this is the person standing inside that lift. The lift is going down. This is the displacement. But the normal force on this person, that normal force will be like this. Normal force is opposite to the displacement. So what will happen? The work done will be a big fat negative number. It will be a negative number. Got it? It is not zero. A lot of people think normal force means, sir, it will do zero work. No, it can do positive work, negative work also. Okay? Let's see if you guys can answer the next question. Imagine there is a lift. Imagine there is a lift accelerating upward, and a person's mobile phone drops down on the floor of the lift. During the fall, work done by gravity, work done by pseudo force. Will it be positive or negative? That is the question. A person is inside a lift and by mistake, the mobile phone slips out of his hand and it falls down on the floor. So in this scenario, will the gravity do positive work, negative work? Pseudo force will do positive, yeah, negative work. Come on, think about it. How are you going to do this? KSR, I hope you read the channel name. It is Vedantu NEET English. Obviously, we will be talking in English, but it is not England English or American English. It is Indian English. Okay, cool. So, my dear students, how are you going to solve this particular question? Think about it. So, first of all, you will just imagine that, okay, there is a lift. Okay, it is accelerating upwards. Okay, there is a mobile phone over here which drops down. So, this is how the displacement will be. There will be two forces on that mobile phone. One is the gravitational force. Gravitational force mg will be downwards. Apart from that, there will be also additionally pseudo force. Pseudo force always acts opposite to the acceleration. So pseudo force will also act downwards. Best part, all of them are in the same direction. That means the work done will be positive by gravity and also positive by the pseudo force. So even pseudo force can do pseudo work. Pseudo meaning, okay. So guys, how many of you have watched this previous lecture? If you have not watched this previous lecture, please watch it. Okay, I'll just show you in the home page only, it will be there. Just go behind. Yes, see this playlist, just go over here, okay. I think it's not been added over here by mistake. I'll just get it added. Newton's laws, we had done Newton's laws. Where did Newton's laws go? Yeah, see Newton's laws. Okay, so this was part 2. Part 1 was also done over here. So guys, watch this particular lecture. I have explained what pseudo force is. It's a fake force which comes in an accelerated frame. Whenever you are in a lift frame or accelerated car, braking train, then the force of inertia, like the force which is opposite to the acceleration, which is not a real force, pseudo meaning fake, it's just on paper, that is called pseudo force. Okay, it is only in accelerated frames. Okay, so I hope you saw the answer is positive for both. Satyashri, it is not negative? Yeah, it is positive. For both the answers, it is positive and positive only. Yep. So this is a tricky question. Many students usually make some kind of silly mistake. That's why I gave this to you. Let's go to the next question, guys, coming up on your screen. Let's go to the next question. Imagine there is a mass of 2 kg. There is a rope and you are pulling it upwards like this, and it happens to accelerate at 5 meters per second square. The question is, what is the work done by the tension? Next, what is the work done by gravity? Next, what is the total work done? What is the total work done in basically let's say 10 seconds, or let's say just 2 seconds. In basically 2 seconds, starting from rest. That is the question. When you're pulling it up, it's going to start accelerating up at 5 meters per second square. How much work will the tension do? How much work will the gravity do? And what's the total work done by all these forces? That is the question. Okay. Work done by gravity does not depend on the left acceleration. No, Shalini, it won't. Because gravitational force will be mg. Displacement is just that displacement from that point till the bottom of the lift. So displacement will be same. Mg will be same. So work done by gravity will not change in that scenario. So let's have a look at this particular question, my dear students. Okay. First of all, in 2 seconds, how much will you displace? Let's find out the displacement. So the displacement can be found out using ut plus half at square. Because without that, we cannot calculate the work. Initial velocity is 0 because you started from rest. Half into acceleration is 5. Time is basically 2. So 2 square. 2 and 2 cancels. 5 2s are 10. So basically you have moved 10 meters. You have moved how many meters? 10 meters. Next, gravitational force, I know. It is nothing but mg. So it is just 2g, which is basically 20 Newton. But tension, I do not know that. So I'll just show some tension over here. And let me apply Newton's laws. As per Newton's laws, this force will be more than this, because of which it is going up. So tension minus the 20 Newton force is mass times acceleration. Acceleration is 5. I've just used net force is ma. F is equal to ma. Therefore, tension will be 2 5s are 10 plus 20. Therefore, tension will be nothing but 30 Newton. Tension will be 30 Newton. Lastly, let's come to the work done part. Work done by tension will be tension force, which is 30 Newton, multiplied by displacement, which is 10. So it will be 300 joules. What about the work done by gravity? Gravitational force is down, displacement is up, hence negative work. Did you understand why negative work? Gravity is down, displacement is up. How much is the gravitational force? 20. Displacement 10. So how much will it be? Negative 200 joules. Negative 200 joules. Lastly, we add them up to get the total work done. 300 minus 200 is basically 100 joules of work. 100 joules of work. Got it? Yes, if acceleration is upward, F net is upward. Yes, Sushmita. Wherever is the acceleration, that is the direction also of the force. Keep that in mind. So actually, net force, I mean. So actually speaking, this came from this Newton's law. Net force is mass multiplied by acceleration. This is acceleration, this is mass. Net force is this minus this, not 20 minus t. Why not 20 minus t? Because it's going up. So this force will be higher than this. That's why it is going up. So t will be more than 20. So make it positive. Always choose the direction of the acceleration as positive. That's a simple way of looking at it. Is that right? Everybody understood these questions? Shall we go ahead? I hope you are building up that confidence on work calculations. These are straightforward questions either on dot product or just finding the sign of the work or just finding the amount of the work and such things. Okay. Now let's go to the next part where the work done has to be calculated because the force is changing. Imagine you are moving from here to here. This is your initial point and this is your final point. You are moving along this particular path. Every point the force is different. Maybe the force over here was like this, here it is like this, here it is like this, here it is like this, maybe here it is like this, here it is like this, here it is like this, and finally maybe here it is like that. Force is variable. So how do you do that calculation? So work done by variable force. By variable force. How do we do that? So what you do in such cases is you take some random snapshot, maybe over here, and let's say, or maybe over here, a small movement where you are displacing by a very small amount ds, and at that moment the force acting is basically F. So I will say the work done to move by a small amount will be nothing but dw, and that dw will be nothing but the force over there into the small displacement at that location. Force into small displacement will be the small work which I have done over there. Okay? Yes. Yes, Lam, Ritu ma'am is also teaching in the DNA batch. Yes, she is teaching biology. Which means if I want to find the total work done from this point to this point, I take small displacement. I see the small work. I add them up. I will get the total work. I did 0.1 joules, then I did 0.05 joules, then I did 0.068 joules. So you add those joules, I will get the total work done. So therefore, I will say that the total work is basically the sum of all such work, okay, for small displacement, for all the small displacements, and when I have to sum it up, it means I have to integrate it. So basically it is nothing but the integration of force with respect to the displacement. That is how we find out the work in a variable case scenario. When the force is changing, when you are not moving along a straight line, so you integrate by going from the starting point to the ending point. The limits of the integration are always from the start till the end, from initial to the final location. We'll take examples so that you understand it. Number two, whenever you say integration, you will always think about areas under the curve, which also means that, say for example, somebody gives you a graph like this and they tell you, listen, this over here is displacement on the x-axis, on the y-axis what you have is the force, and let's say the graph of the force happens to be something like this. then the area under the curve gives me the work done from the start till the end. But just like areas under the curve can be positive, negative, the work done can also be positive, negative accordingly. So, say for example, you happen to measure this area which is above the horizontal line. Because it is above, it is considered as positive area. Even this part right over here, this is considered as positive area, whereas this one over here, which is below the horizontal line, is considered as negative area. The moment you go down, it's considered as negative area. So this one over here is considered as positive work, with the ones where force is above the displacement graph, a displacement line, and the ones where it is below, it is considered as negative work. So I can also say that over here, work done is nothing but the area under the force versus displacement graph. Area under the force displacement graph also gives you the work done, one and the same thing. Let's take examples on this. Imagine I tell you something like, there is a force which is given by 3x minus 2 Newton. Find work done by it. Find the work done in moving it from x equals to 0 to x equals to 2 meters. How much work will be done in this scenario? Let's try to solve this question. Okay. The moment I look at this question, I see force is 3x minus 2. 100% it is a variable force. I can use any other function also. There is no need that I should use 3x minus 2. Just imagine if it was something else. Just imagine if it was not 3x minus 2. Let's say it was something else. Let's say it is x cube, 2x cube. This is also variable force. 2x cube minus sine x. As x changes, force changes. So all these are basically examples of variable forces, where force changes as you move. Like spring force, when you elongate a spring, the force keeps on changing. So at different places, the forces are different. That is a variable force. So say for example, we have to solve this question only. Let's get rid of this then. So how do you do this? Work is integration of force with respect to displacement from initial point to final point. Our force itself is 2x cube. Displacements are happening in the x-axis, so I'll just put dx over here. Next important thing, initial point and final point means the coordinates. Initially I was at 0, finally I was at x equals to 2. So initial coordinate of x is 0, the final coordinate of x is basically 2. The limits always come of the same variable which is there inside the integral. If this was y, then I will put y coordinates. If this was z, I will put z coordinates. Here everything is happening in 1D, so you don't have to worry. You'll be like, sir, what if I get a 2D question? Don't worry, we'll solve that also. Alright, so let's solve this integration. First of all, 2 is a constant, so bring it outside. X cube's integration is x raised to 4 upon 4. X raised to 4 upon 4, limits are 0 and 2. What will happen? Work done will be 2 and 4 cancels. 2 and 4 cancels. You will have 1 by 2 over here. You will put 2 over here instead of x, so it will become 2 raised to 4 minus. Put 0 instead of x, so 0 raised to 4. That's it. So 2 raised to 4 divided by 2 is basically 2 cube, which is basically 8 joules. Is basically 8 joules. So very good VS Vetri. Awesome. Very good Vaishali. Kudos to all of you. Yes, that is the correct answer. Yes, Satyashri. Not Newton, it is joules. So this is how you can calculate by a simple integration. Let's do one more question, but instead of x, let's also bring in y now. Both x and y will be there. Okay. So get ready for the next question where both x and y are there. Imagine I tell you our force is given by x I cap minus 2y square j cap Newton, and our initial location is basically 0, 1, and our final location is, let's say, 2, 3. Okay, so the question is basically find the work done. Okay, so that is the question. Let's try to solve this. Oops. Find the work done. As you can see over here, both I cap and j cap, both x and y are there. Both the coordinates are given for initial and final location. Let's start with our basics. Work done is basically integration of force dot displacement. But whenever there is 2D question, remember what you will do is, look at this. Force is nothing but x I cap minus 2y square j cap Newton. Displacement, don't put it as ds. Don't put it as dx also, because it is not moving in x. It is moving both in x and y. So that small displacement will be dx I cap plus dy j cap. That is what you will have to put. Understand why this comes. When you are moving a small displacement like this is your displacement ds. It will have some displacement in the x-axis, some displacement in the y-axis. This will be dx, this will be dy. So dx I cap plus dy j cap gives you this displacement vector. Got it? Understood? Now do the usual dot product. When you do the dot product, I cap will multiply with I, j with j. So you will get x into dx will become x dx. This into this will become minus integral 2y square dy. That's all. Minus 2y square into dy. J into j is 1. I into I is also 1. X into dx is x dx. Now when you do the limits, be careful. For x, put the limits of x coordinate. X coordinate starts from 0, goes to 2. Y coordinate starts from 1, goes to 3. That is the catch. If you mix and match, you will get a wrong answer. It will be a silly mistake then. Okay. X's integration is x square by 2. Limits are from 0 to 2. Minus 2 is outside. Y's integration is y cube divided by 3. Limits are from 1 to 2. So what will the work be? Let's find out. First put 2, then put 0. So 2 square minus 0 square divided by 2. Minus 2 by 3. Minus 2 by 3. First put 2, then put 1. So 2 cube minus 1 cube. So 2 square is 4. 4 minus 0 is 4. 4 by 2 is basically 2. Minus 2 by 3. 2 cube is 8. 8 minus 1 is basically 7. So basically this is what I will get. You can, if you want, take 2 common. 1 minus 7 by 3 is what you can do. Okay, so this will become 2 into 3 goes on the top. 3 minus 7 is basically minus 4 by 3. So guys, the answer will be minus 8 by 3 joules. So the answer is coming out to be negative. Got it? Yep. Yes. Oh, second one, I had to do it from 1 to 3. My bad. I think I did a silly mistake there. Sorry. While copying it down, sorry. This was y cube, this was 1 to 3. Yep, sorry. So this was 1 to 3. So this will be work done. Okay. First put 2 over there. So 2 square. Then put 0 in place of x. 0 square by 2 minus 2 by 3 over here. And then put 3 over here. So 3 cube minus 1 cube over here. 2 square is 4. 4 minus 0, 4. 4 by 2 is 2 minus 2 by 3. 3 cube, guys, is 27. 27 minus 1 is basically 26. So this will be nothing but 2 common. 1 minus 26 by 3. Now 3 minus 26 is basically minus 23 divided by 3. So this will become minus 46 divided by 3 joules. Minus 46 by 3 joules. Just check this out. Yep. Understood, guys? Clear? How to do these kind of questions? Shall we go ahead? Shall we go ahead? Yep. So whether it is in one dimension like this, when it is very simple, then you just multiply it with dx, integrate it in that one single dimension. Similarly, when it is in two dimensions, be careful that displacement, don't put it as dx nor dy, rather put it as dx I cap plus dy j cap, because that displacement is itself made of two components. So that is the catch, and then do the dot product. I cap with I cap, j cap multiplies with j cap, and then continue to solve the problem. Let's do the next question. Here the question says the mass is given to be 2 kg, x is given to be t cube meters. Find the work done in the first 2 seconds. Find the work done in the first 2 seconds. That's the question. Let's try to solve this. Mass is given, position is given, force is not given. You might be wondering, sir, force only is not given, sir. How do we solve the problem? So try to find the force. How do we find the force from x? See, for force I need acceleration. For acceleration I need velocity. For velocity, oh, I can differentiate x. Exactly. So take the derivative of x, you will get velocity. It is nothing but dx by dt. So it will be nothing but derivative of t cube, which is nothing but 3t square. Okay. So acceleration is just derivative of the velocity. Derivative of the velocity means derivative of basically 3t square, right? So 3 comes outside and you will be multiplying it with 2t, which is basically 60. Force is nothing but mass times acceleration. Mass is given to be 2. Acceleration is given to be 60. So hence it will be nothing but 12t. Okay. So the force is given to be 12t. Interesting. But again, then there is a problem. Force is not a function of x, it is a function of time. Let's see what to do with it. But for now, work done is nothing but integration of force. Everything is along the x-axis, so I'll just multiply it with dx from initial to the final point. Force is 12t. But I can't integrate it with respect to dx. Do you see that? Why? Because whenever time is there, you have to have dt. Whenever x is there, you should have dx. If z is there, dz. If some other variable like, some p is there, you should have dp. So guys, this integration is not possible. So you'll be like, sir, how to do this? Isn't it much more difficult now? Yes, it is now difficult. There is an easy way to solve this problem. So you can't integrate it beyond this. There is a very interesting method to solve these problems, these kind of questions, in a very simple manner. And that's why we are going to the next part, which is the work-kinetic energy theorem. Work-kinetic energy theorem. So what is this work-kinetic energy theorem? First of all, let's understand what is kinetic energy. What is the meaning of kinetic energy? Do you all have kinetic energy? You will be like, maybe sir, if you stand on some other planet and look at us, you will see the earth moving. So all of us are moving, so we have kinetic energy. If you are on earth and looking at us, then we are at rest, sir, so then we don't have. But if I start running, then I have energy of the motion, which is again kinetic energy. So simply put, kinetic energy is the energy possessed by a body just because it is moving. And you can feel that energy. Anything thrown at you, it has energy, because when it comes and hits your face, that's it. You feel that impact and all that energy gets transferred to you. Anything under motion has kinetic energy. So the energy possessed by a body is the energy possessed by matter on account of its motion. On account of its motion. The formula for kinetic energy is simply put half mv square. Is just nothing but half mv square. But some people also like to write it in slightly different forms like this. Half into m into v, square both m and v. So because you have put an extra m on the top, you need to put an extra m below. So now if you notice, I can just write this as mv square divided by m. What is this mv? Technically this mv is nothing but momentum. So I can also write it as half p square by m. So this is also kinetic energy, guys. This is also kinetic energy in a alternate formula. Half mv square or half p square by m. Both are the same thing. Just like before, work was a scalar, even kinetic energy is also a scalar quantity, and it is also measured in the same unit. Either you use joule or you use erg if it is CGS. This is SI, this is CGS. This is also scalar. This is your basic formula and meaning of kinetic energy. This mass into velocity was nothing but momentum. In your modern physics, later on you will see this formula gets modified and you will probably notice things like this. K into 2m is equal to p square. Therefore, the value of momentum will be root of 2 times mass times kinetic energy. It's just the same thing. Just shift that 2m with k. 2m into k under the root will then become momentum. So this can be also alternatively used whenever required. So say for example, there were some questions in the NEET examination, something like this. If the momentum is tripled, the kinetic energy dash by dash percent. The kinetic energy increases or decreases by how much percent? Let's see if we can solve this question. These kind of questions are very, very popular in the NEET examination. Relation between momentum, mass, speed and kinetic energy. So is momentum related to the kinetic energy? Yes. So if my original kinetic energy was K, original momentum was P, so it will be P square divided by 2m. This was your old. What about the new kinetic energy? I'll call it as K1. Will be the new momentum square divided by 2m. But wait a minute. The new momentum is 3 times the old momentum. So it will be 3p whole square divided by 2m. 3 square is 9 and into p square divided by 2m. P square by 2m is just k. So basically 9 times of the old kinetic energy. The new kinetic energy is 9 times the old kinetic energy. Now how do I find the change? So first of all, it is increased 100%. It has increased for sure. But by how much percent? Come on, put up the answer in the chat box. Let's see if we can figure out whether it is 20%, 30%, 100%, 200%, 500%. What do you think, guys? The percentage change in the kinetic energy is always how much is the change upon how much is the original. And because you're calculating percentage, you always multiply that fraction with 100. The changes from 9k and k, the difference is basically 9k minus k. Original value of kinetic energy was k multiplied by 100. 9k minus k is basically 8. K gets cancelled, multiplied by 100. So guys, the change is basically 800%. So it changes by 800%. Many people end up saying the answer is 900%. No, it is the change which is asked. So it changes by, the kinetic energy increases by how much? 800%. So be careful in such questions. So the change was this minus the old one, 9k minus k, which was 8k. Cool. So now that you understood kinetic energy and now we have to still solve this particular problem, let's solve it, guys, by using this theorem. What is this theorem? This theorem is called as work kinetic energy theorem. Work kinetic energy theorem. This says that the total work done by all forces in and on a system changes its kinetic energy. Very simple. The total work done by all the forces changes the kinetic energy. For example, I am taking this book, I am lifting it up, I am doing some work. As I move it up, I can see it has gained kinetic energy. Why? Because I have done positive work. So I did positive work, it increased its kinetic energy. Somebody threw a book at me, so that book is coming at me, so I'm trying to stop it and I slowly stop it. I suck away all the energy. My force is here, displacement is here, exactly opposite. The book was coming like this, I stopped it. So force was opposite to the displacement, negative work, so kinetic energy also decreased. I'm just carrying the book like this. The force is perpendicular to the displacement. The force is up, displacement is horizontal. It is not doing work, so the body will maintain its kinetic energy, meaning there will be no change. So this is exactly what this statement says. If you do work positively, kinetic energy will increase. If you suck away that energy, basically do negative work, the kinetic energy will decrease. And if you do not do any work, then there will be no change in the kinetic energy. As simple as that. So statement wise, it goes like this. The total work done, whether by internal plus external forces, will be nothing but final minus initial kinetic energy, or you can just call it as change, which is delta K. That is what this is. That is what this is. So you'll be like, sir, very great. How will this help me solve this question? You might be wondering. How will we solve this particular question? Let's do it. I just created a duplicate of this. Let me probably just remove few parts. I had to find the work done, right, in this question, and I was stuck over here because time can't be integrated with x. No issues. I don't do this only. I just stop over here. I got velocity, and I think that is actually enough. Let me find the velocity when time is 0. That means it will be 3 into 0 square, which is basically 0 meters per second. What will be the velocity when time is 2? So 3 multiplied by basically 2 square, 3 into 2 square, which is nothing but 3 into 4, which is 12 meters per second. Now what is the question? Work done. Can I not find the change in the kinetic energy and then solve the question? I think it will be easy then. How? Observe. Work is nothing but final minus initial kinetic energy. Therefore, work will be final, will be half into mass, which is 2. Velocity finally was 12, so 12 square, minus initial kinetic energy, half, into mass, which was nothing but 2, into initial velocity, which was nothing but 0 square. So guys, what do we get? 2 cancels, 12 square is 144. This is nothing but 0. So hence the answer is 144 joules. We got the answer without even integrating. We got it like this using work kinetic energy theorem. Isn't it amazing? Yes, Shruti Yadav, this is the first class for the chapter. And if you have missed the starting part, Shruti, just go back even in the live class. Right from the basics I have started. Okay? Great. I will show you one more example, guys, for work kinetic energy theorem. Just let's probably go back over here. I hope you remember this question where we had to find the total work done, and we did it by finding the displacement using this equation. We found the work done by tension, gravity. These were asked separately, and then total work also. So Just imagine over here, if we do it using work kinetic energy theorem, how we can find the total work. First of all, let's use, see, we need velocity. Why? Because we need to find kinetic energy. We are using work kinetic energy theorem. To find velocity in 2 seconds, I will use kinematic equation. V is u plus at. Initial velocity 0. Acceleration 5. Time given to be 2 seconds. So it will be 10 meters per second. That is the velocity. This is basically final. Initial velocity was 0 because it started from rest. So in order to find the total work done, it will be nothing but final minus initial kinetic energy. Final will be half into mass is 2, velocity was 10, initial half into mass, initial velocity was 0. So guys, 2 cancels, 10 square is 100. This is nothing but 0. So the answer is 100 joules. Exactly the same what we got over here. It's no different. Obviously, work kinetic energy theorem also gave the same answer. Normal method using Newton's laws and kinematics also gave us the same answer. It just shows that, work kinetic energy theorem works. Is this amazing, guys? Super. Loved this application. Cool. Shall we go ahead? Yep. Shall we go ahead, guys? All right. So let's solve another question, guys, coming up on your screen. This is a force versus displacement graph. One is a triangle, one is a rectangle type. Question is, find number 1, total work done in 12 meter displacement. Number 2, the final speed of a 4 kg mass at x equals to 12 meters. These are the 2 questions which have been asked. Let's see if you can figure this out. First part is very easy. Find the total work done from here till here. Second part is, we'll think about it. To find the total work done when force displacement graph is given, what do? You find the area under the curve, isn't it? You basically find the area under the curve. Yes, that's what we have seen. Work done by variable forces. Where is it? Right over here. You find the area under the force displacement curve. Anything on the top is positive, anything below is considered negative. So let's do the same thing here as well. First of all, over here, this is a triangle. So area of a triangle is half into the base, which is 8 meters, multiplied by the height, which is basically 6. So 8 by 2 is 4, 4, 6 are 24. So this is 24 joules. If you talk over here, the work done will be negative. It is negative area of that rectangle or the triangle, whatever you call it. No, sorry, square. This will be what? Minus this one over here is actually 4 meters. 4 meters. 8 to 12 is basically 4. Height is also 4. So 4 into 4. So this will be minus 16 joules. Minus 16 joules. Exactly. So therefore, the total work done will be 24 minus 16, which is 8 joules. So that is the work done. So first answer is done. First answer is done. Okay, don't add the areas, always subtract. Yeah, 24 minus 16, don't add it or else you will get 40. Yeah, so that is wrong. Be careful. Negative area, anything below is negative. What about the second part? We know that the work done is nothing but final minus initial according to work kinetic energy theorem. Perfect. Final is half into mass, which is 4, into speed, speed which I don't know. Initially, it was maybe at rest, so half into mass into 0 square is equal to 8. This is 0 is equal to 8. 4 by 2 is 2 and this is nothing but V square, right? Half into mass into V square is the kinetic energy. Change in the kinetic energy is the work done. So 2 and 8 cancels and I will get V square as 4. So V is basically 2 meters per second. So over here, this mass will have a speed of 2 meters per second. So this is how you can use work kinetic energy theorem in different questions. Is that clear, everyone? Cool. Shall we go ahead to the next one? Shall we go ahead to the next one, my dear students? All right, let's do this. Look at this particular question. There is a mass of 4 kg. It's going on a surface which is rough, having coefficient of friction 0.2. It already has a speed of 10 meters per second. And finally, it comes to a stop. Question is, what is the stopping distance? What is the stopping distance? Now, ideally, this problem you can solve it even using Newton's laws and kinematic equations. Like you can say, okay, sir, see what will happen is that block which is there, it will experience multiple forces. One force will be the gravitational pull down, which is 4g. Then there will be a normal force like this. And then there will be friction, which is kinetic in nature, which will be like this. And this kinetic friction will be mu into n, mu being 0.2, normal force being 4g. So g is basically 10, shifts the decimal, 2 4s are 8. So kinetic friction will be 8 Newton. It will act against our displacement. Against our displacement. So it will cause some retardation. You find that retardation, then use kinematic equations and all that to find the displacement and then find the work done. It is one way of doing it. This is one way of doing it. Rather, there is another way of doing it. I'll tell you how. Use work kinetic energy theorem. As per work kinetic energy theorem, the total work done is final minus initial kinetic energy. Right? That is what the work kinetic energy theorem says. Is normal force doing work? So there are three forces: work done by normal, work done by gravity, work done by friction. Is final minus initial. Is normal force doing work? Think about it. No, right? Why? Because it is perpendicular to the displacement. Even gravity is perpendicular, so that is also not doing work. So guys, the good thing is normal and gravity both are doing zero work. So how about putting 0 plus 0 over here? 0 plus 0 over here. Clear? What about friction? Friction acts against the displacement, so it will do negative work. How much negative work? Frictional force into the displacement. Frictional force is 8 Newton multiplied by the displacement, which is x, which I do not know. How much ever displacement it does till it stops. What is the final kinetic energy? It is 0. What is the initial kinetic energy? It is half mu square. So it will be negative half into mass, which is 4, into speed, which is 10. So guys, minus minus will cancel. So I will just have 8x. Okay, 4 by 2 is basically 2. 10 square is basically 100. 2 and 8 cancels. it will become 4, 4 goes below, so it will become 100 by 4. So therefore, x will just become 25 meters. So see how easy it is to solve the problem using work energy theorem. Imagine you did not have access to this theorem, then it will be so lengthy. You will first draw that free body diagram, then again you will find that frictional force, okay, and you will find the frictional force is 8 Newton. Then from that you will try to find how much retardation is there using F is equal to mass into acceleration. Force is 8, mass is 4, acceleration is basically 2 meters per second square. From that you will again try to find how much is the displacement, which is ut plus half into at square. Initial speed is 10. Oh, but I do not know that time. Okay, so what I will do is I can use v square is u square plus 2as. Final speed is 0, initial speed is 10, acceleration is negative 2, and displacement is x. From this you will find x, and from this you will find work. That's it. Work was not needed, but basically from this you will find basically x. So you had to find acceleration and then you had to find x using kinematic equations. But we have completely avoided that using work kinetic energy theorem. Cool? So that is the application of it. Awesome. Now, before going ahead, let us see there are two kinds of forces based on how they work or what kind of work they perform. There are two kinds of classification of forces. Like that, there are many ways to classify forces. Gravitational force, electric force, etc. Right? So there is one more way in which you can classify, just like you learn classification of plants and animals, right? Vertebrates, non-vertebrates, this, that. So same way we can classify force based on how they work or based on how they perform work. Let's take an example to understand this. Imagine there is a 2 kg mass. I move it like this, 4 meters, and then I move it like this, let's say 6 meters, and I reach over here. Okay, I have gone like this. In this process, while taking it up, gravitational force is down, so gravity will do negative work. How much negative work will be done by the gravity? In the first part, minus, because force is down, mg is the force, so 20 Newton multiplied by the displacement, which is 40, so it will do minus 80 joules of work. Remember, gravitational force will be 20 Newton or 2g or 20 Newton. Okay, so 20 Newton force here. In this path, the gravitational force is perpendicular, so the work done by this gravitational force in this second part will be 0. In this entire process, the total work done by the gravitational pull came out to be minus 80 joules. Now let's do one thing. Let's take it some other way. Let me take it here, then here, then here, then here. Like this, let's say I move 10 meters. Like this, let's say I move maybe 7 meters. And like this, I'll have to move back 4 meters, and 7 to 4, that is 3 meters over here. 10, 7, 4 and 3. In each part, how much work am I doing? In this case, gravitational force is perpendicular, so 0 joules. In this case, gravitational force of 20 Newton is against the displacement, so that's why negative work done. So minus 20 into 7, which is minus 140 joules. Here, the force is again perpendicular, so 0 joules over here. Here, the gravitational pull is in the same direction. So 20 Newton is in the same direction. So how much will it be? It will be 20 Newton into 3, which is basically plus 60 joules. if you ask me what is the total work done by gravity, it will be nothing but minus 140 plus 60, which is going to be minus 80 joules again. Wow, this is crazy. It came out to be the same answer as before, even though I took a longer path. And now you can try out as many paths if you have a lot of time, if you're jobless, you have holidays, you have vacation, you try out any path, you will always find the answer to be the same as long as the same mass is there, same initial point and same destination. So here we saw that the work done by gravity was same for all the paths. Same for all the paths. Let's take one more example. Let's take one more example to understand it. Say, for example, this is the top view. Maybe there is a table or something like this. This is the top view of a table, and maybe there is a box over here. Maybe there is a box over here. And this box has to be moved in multiple different ways. So first time, I move this box like this, and then I make it go over here. Maybe this is, for example, 4 meters, and this is 3 meters. While I move this box, remember, friction will act, and the frictional force is going to be like this, opposite to the motion, opposite to the motion. So as I move from here to here, the frictional force, the kinetic friction will act. Maybe let's say it is 10 Newton force. Maybe it is 10 Newton force. As I move and change the direction, instead of going like this, I move like this. Then the friction will also change the direction, and the friction will then act exactly like this. So again, the kinetic friction will be applying a force of 10 Newton in this direction. If you ask me how much work was done from here to here by the friction, the work done by the friction in the first part of the problem was negative because force is opposite to the displacement. Force was 10, displacement was 4. So it was minus 40 joules. From here to here, in the second part, if you ask me how much work was done, then it will be negative again because force and displacement are opposite, minus 10 into 3, which is minus 30 joules. If you ask me how much was the total work done, it will be minus 40 minus 30, which is basically minus 70 joules. Did you see that? Minus 70 joules of work was done. Okay. Now let's do one thing. Let's take this same mass like this. How much will be the length of this? If this is 4 meters, this is 3 meters, 100%, this is 5 meters. This time, the kinetic friction will act like this. The kinetic friction will act like this of 10 Newton, whereas our displacement is in this direction. If you ask me how much is the work done in this scenario from here to here, it will be negative. Force is 10, displacement is 5. Therefore, the work done is negative 50 joules, which is way different. It is not vertical. This is the top view. Just imagine there is a table like this and I'm seeing it from the top. I'm seeing it from the top. This is a top view. So friction is acting along this particular plane. Is that okay? This is a top view. Shalini. Those of you missed this part. This is the table top view. I hope now it makes sense. Cool? Clear? Great. So now, what do you see? The work done. So the work by your friction depends on the path. Depends on the path which has been taken. Depends on the path which has been taken. Is that clear? So naturally, we have now two different categories of forces. Forces whose work does not depend on path, which is very good for making our calculations easy. Imagine there is some crazy path. I can simplify it by choosing my own convenient path. So it makes our job easy. The work done is independent of the path taken. And then there are those other kind of forces where you change the path, it will depend on how you went there. It is like in your thermodynamics of chemistry, you have something called as state function and path function. Do you remember these terms? Pressure, volume, temperature, they are our internal energy. They are your state functions, whereas work, heat are path functions. How many of you remember this? It's exactly like that. So that's how we get this classification over here. The first type is basically called as conservative forces. Conservative forces. The second type is then called non-conservative forces. Examples of conservative forces. Yes, examples of conservative forces, like I said, gravitational force. Just like gravity, even electrostatic force is also conservative. Electrostatic force is also conservative. Even you will see spring forces, elastic forces, they are all conservative in nature. Non-conservative forces are like frictional force. Frictional force. Just like friction acts between solid-solid surface, liquid-liquid friction is called viscous force. Liquid-liquid friction is called viscous force. And when you are moving in air and in a fluid, or a ship is moving in water, solid is encountering a liquid, aeroplane is going in wind, the air applies a drag force. So you also have a drag force by the air or the liquid or the fluid in general. Even normal force and even tension force, these kind of forces decide, the work is decided by the path taken, okay, not just the destination and the source. So they are non-conservative forces, right? These are all evil forces, these are all good forces. So work done is independent, very, very important, independent of the path, So go like this or like this. This work and this work will be the same for the same initial and the final source and destination. Here the work done depends on the path taken. So if you start over here and go like this, you take W1 work to reach from here to here, you go some other way, you will see some different work will be done. Also, if I come back to the same point, the net work done will be 0 because the displacement will be 0 in this case. So for a closed path, work done is 0. Very, very important. That means you come back to the same point where you started, then you would have 100% done 0 joules of work because there is no net displacement. Makes sense. But here the closed path work is not 0. Closed path work is non-zero. Very, very important. Here it is 0. So if you come back to the same point right from the beginning, this answer will not be 0 joules for non-conservative forces. Is that clear? Okay. Now let's take an example on this conservative, non-conservative forces. Imagine you start from this point, you go to this point, another point over here, another point over here, another point over here. It's told to you If you go from A to B, you will take 10 joules of work. If you go from C to B, you will take 20 joules of work. If you go from E to D, then you will take minus 10 joules. If you go from D to C, you will take 50 joules of work. Question is, how much is the work done to go from E to A if the force is conservative? If the force is conservative in nature. Come on, think about it. Not that difficult at all. From each point to the next point, the work done is given. If you want to go from E point to A point in this conservative force environment, how much will be the work done? Stuti will be having other classes chapters every week. You can see the whole lineup is there already on the channel. Whatever classes are there, right, for this particular coming week, it will keep on getting updated. Like we have NCRT series in the evening, and in the afternoon time we have the RNA series. So we have almost like on an average 2 classes on the weekdays, okay, and Sunday time we give it for your test, assignment, backlogs or practice PYQs, whatever you want to do. So on the weekdays you can see all these classes are lined up already, yep, and this will keep on coming up, okay. So all the 4 subjects: physics, chemistry, botany, zoology. All right, let's see how to solve this question. I know the total work done in a closed path should be 0. So work done from A to B plus B to C plus C to D plus D to E plus E to A, the whole thing should be 0 because you have come back to the same point, started here, ended here. What is the work done from A to B? A to B is 10 joules plus C to B is 20, so B to C will be negative 20. C to D will be negative 50 because D to C is plus 50. So opposite, so the sign will also change. D to E will be negative of negative 10, which will make it plus 10. Finally, will be work done from E to A will be 0. 10 minus, okay, first let's add all these numbers. Minus 20 and minus 50 is minus 70. 10 and 10 is 20. So I'll just have 20 minus 70 plus work done from E to A is 0. So 20 minus 70 is minus 50, guys. Minus 50, right? So therefore, the work done from E to A will be plus 50 joules. How many of you got it? Just check this out. Just check this out. See if you made some silly mistake anywhere. Most likely some of you made some silly mistake. A to B, 10. Okay. B to C, negative 20. C to D, minus 50. D to E, negative of negative, which will make it positive. Minus 20 minus 50 is minus 70. 10 and 10, 20. 20 minus 70, minus 50. So take it on the other side, it will be plus 50 joules. I think some of you made some silly mistakes somewhere. See where you made that mistake. Okay, cool. Awesome. Great. So that was your conservative and non-conservative forces. But there is one more thing attached to conservative and non-conservative forces, which I have not given here, which I will put up now. Why they are called conservative and non-conservative in the first place? Why they are called conservative and non? Why that name? We understood what they mean, but why that name came? The reason why their name came is because of how they behave when they are brought back to their original state. Today, you give some person sitting beside you, hey, listen man, I can't carry all these books today to my home, and some chocolates are also there. My mom is there at home. I bought so many things for Champa. So if my mom finds out about these chocolates, my mom will hit me. So, I want to give Champa tomorrow all these chocolates. You give it to your friend. Next day you ask, okay, did you bring back those chocolates? Champa, I want to give. Friend is like, I ate those chocolates. You will be like, what the hell? Such a kind of force is called non-conservative. You did not conserve anything, not loyal. You give your friend chocolates, you will be like, listen bro, I need to give Champa chocolates, get it tomorrow back. I can't keep it in my house. Your bro gets back all those chocolates. You give it to Champa. Champa happy, friend happy, you happy. Conserved everything, conservative force. You will see whenever things like gravity, electrostatic, all these are good forces, spring forces. They will conserve the energy of the system. But these forces, normal, tension, viscous, friction, drag, all these forces, when they come, they suck out the energy from the system and they take it away. So that is why the name has come. So basically, they conserve energy. They conserve energy by storing and relieving faithfully. Here, they don't conserve energy. They don't conserve the energy. Either they add or suck out the energy. Suck out the energy from the system. Also, one more thing. Sir, but work is a scalar, but they are negative and positive. Shalini, even charge is a scalar, but charge can be positive and negative. See, what happens in school, we have been told vectors, they have sign, positive, negative. Scalars, no sign, only magnitude. See, just because it has value does not mean it is always positive. It can be 0 also, it can be negative, it can be positive. So just because something has a sign does not mean it has a direction. Just like charge. Charge has positive charge, negative charge. Does it have direction? No. Current, does it have any meaning in vectors? No. Right? So current can be positive, negative. Same way, even work can be positive, negative. Power can be positive, negative. Does not mean they are vectors. It's just, telling whether you are giving or taking. It means something. That positive or negative means something else. In case of work, it tells whether you are giving or taking. That's all. It is not telling me the direction of anything. Great. One more thing, because all these kind of forces, you might have seen energy is conserved. These forces have some energy associated with them. You would have heard about gravitational potential energy. In 12th standard, you will hear the word electrical potential energy, or maybe even in 10th. Spring stores energy. Even elastical energy you would have heard. But never will you hear drag energy, viscous energy, frictional energy, normal potential energy, tension potential energy. Have you heard these words? Like frictional potential energy, viscous potential energy. Clear? So guys, I can say that potential energy is associated. No potential energy is linked to these kind of forces. You will never hear the words like frictional energy, potential, etc. But you will hear words like gravitational potential energy, elastic potential energy, and so on and so forth. Got it, everyone? Till this point clear? Shalini, I hope now you have understood after that example. That confusion should not be there. All right. So till now, whatever we have learned is work, kinetic energy, and the different types of forces. We'll take a small break. We will return, we'll continue, and we'll complete this chapter, because we just have to do potential energy and mechanical energy conservation along with power. So guys, we'll meet after the break. Okay. So we have done work, kinetic energy theorem, right? We have done work by variable force. We have done types of forces, right? We have also done kinetic energy. All these things are done part, right? So after the break, we will do potential energy, mechanical energy conservation, and also we will do power and relation between potential energy and force in the curve. So these are the things which we will be doing after the break, right? So we will be doing this later on. Just take a break and we'll return. Okay, quickly grab your lunch. Maybe we can meet after, let's say, 18 minutes or something. Welcome back. I hope I'm audible and visible. I hope you had your lunch, guys. Time to complete this chapter. Remaining parts: potential energy, mechanical energy, power. Right? Ready for this? Quickly, and let me know if you have already smashed the like button and subscribed to the channel, marked your attendance already, and get back all your friends. Yep, Shreyas Sir is back. Hi Tanuja, hi Atluru, hi Vetri. Thank you, Sarah. Serotonin. Oh my god. Isn't that some kind of a chemical which is released under, I don't remember biology so much, but yeah. What does serotonin do, guys? All right, Sneha, ready? Very good. Great. Welcome back. Welcome back. Hi, Krishna. I hope you are doing fine. Hi, Vaishali. Ready? Okay, great. Welcome back, Sukanya. Chalo. Okay, time to begin. Where were we? We have done work. We have such a nice diagram, yeah, video. We have done work. We have done the signs of work: positive, negative, zero. We have also done work done by variable force, area under the graph, what is kinetic energy, and also work kinetic energy theorem, conservative, non-conservative forces. Okay. Now, serotonin, melatonin, tryptophan. Wow. Okay, guys, I'm not that great with bio. So, let me tell you, what is potential energy? Now, there are different kinds of potential energy, but there is one thing which is common. Please remember, I'm not talking about gravitational potential energy. I'm just talking in general, any kind of potential energy, be it elastic, electric, magnetic, spring, gravitational. In general, potential energy is because of the manner in which it has been arranged, because of its configuration, because of its state, because of its situation. Like when I take a box on the top of a building, because of the situation, it stores some energy. When I elongate a rubber band, because of its situation, it stores some energy. When I take a spring and I compress it, because of its situation, it stores an energy. I take a steel scale and bend it, it stores energy within it because of its configuration, because of its situation, because of its state. That is called as potential energy. And when the state changes, that means I have pressed it a lot, I release it, or I have bent it, I bend it more, or I take that box on the top of a building and I take it more higher or lower. I change the situation, the potential energy also changes. So it's an energy due to its configuration, or basically state. If the configuration changes, you will see the potential energy also will change. Usually the symbol for potential energy will be U, and delta U is for basically the change in the potential energy of the system. It is also a scalar quantity, keep that in mind. And unit wise, again the same thing, guys. It has joules in SI or ergs in CGS system. U is the symbol, delta U is the symbol for the change. It's a scalar quantity like work kinetic energy, and it is measured in joules or in ergs. There are different forms or manner in which you can store this potential energy, and namely, one is gravitational, you have electrostatic potential energy, you have spring energy, you have elastic energy, etc. Basically, I can say all conservative all conservative forces have potential energy associated with them. Associated with them. All the conservative forces have some or the other kind of potential energy associated with them. Gravitational potential energy, spring potential energy, elastic potential energy. Non-conservative forces like friction, viscous, tension, normal, they do not have any potential energy associated with them. Right. Now, to go further, see, this potential energy in itself has no meaning, but it is always the change of the potential energy which has meaning associated with it. Let me explain this, but first let me write down the statement. Delta U has significance, but U value doesn't. Rather, I would say any configuration or state can be assigned as 0 joules potential energy, which is also called as the zero configuration. What does it mean by this? Observe carefully now. Say for example, somebody took one box and they moved it from here to here, okay, like this. This is the final destination, this was the initial position, and they moved it like this. In this process, the potential energy will change. Gravitational potential energy will definitely change. One Pandu said, listen sir, this right now has 0 joules of energy. When you bring it on the top, sir, it gets 20 joules of energy, sir, gravitation. I'll be like, okay. So when I say the box has 0 joules of energy, it does not mean it actually has no energy. It means I have assumed that when the box is here, it is 0. I have assumed some situation like the box being here as 0 joules of energy. With respect to this box over here, when placed, has extra 20 joules. Which means for some other Pandu who says, no sir, for me, this is 0 joules of energy, then this box over here will have negative 20 joules of energy. Notice from here to here there is a jump of plus 20. This is negative 20 to 0. So again there is a jump of the same number of joules. So you can choose what you want to be called as 0 or like the origin. Okay, accordingly the other values will change. But what didn't change is the change of the potential energy. Delta U did not change. Somebody else might say, no sir, for me somewhere here it is 0 joules. So this is 5 joules sir, this is minus 15 joules. That person is also correct. For them, this is your 0 reference. Somebody else might say, no sir, for me something else is 0 joules. Sir, for me this is 0 joules. Sir, this is 2 joules. So here this will be 22 joules. So for them 0 joules reference is somewhere else only. So the reference point might change, but the change value will remain same, and that is what is important to us. The value of potential energy is not important to us. Is this absolutely clear? So in all these examples, delta U came out to be 20 joules, which was same for all and is important for solving problems. This value is not important, this value is not important, the difference is important. Keep that in mind. Yep. Right? This is something which you should definitely understand. Now, the next important thing. Say for example, I want to calculate how much potential energy is there. You will be like, sir, I know it is mgh. See, mgh is for gravity. But what about spring? What about elastic, what about electric? Is there a general way to calculate potential energy? The answer is yes. I'll tell you how. See guys, say for example, again, I take some mass and let's say it is 3 kilos and I take it up by 5 meters. I take it up by 5 meters. In this process, the gravitational force is acting downwards and it will be 3g, which is basically 30 Newton. Displacement is upwards. So if you ask me what is the work done by gravity, you will say, sir, the gravity has done negative work because the force is opposite to its displacement. So force is 30, sir. Displacement is 5, sir. So it is minus 150 joules. Now tell me, if gravity has done negative work, that means it has taken out energy from the ball. Whatever energy it had, it has sucked it out. So gravity sucked out that energy. Gravity took out 150 joules of energy. But where did it go? Where did it go? Think about it. Yeah, why negative? Which negative? Which means this one, this negative, I've just chosen some random value 0 over here. So that means the change should be 20. So this should go on the negative side. If this is 0, this is plus 5, this is minus 15. Difference between them is 20. Difference between them is 20. 0 is somewhere else. Here the work done will be negative because the force is opposite to its displacement. Where is this work which is done, which means the energy which has been sucked out, going? It is not going anywhere. It is stored properly. So I will say 150 joules was taken from the ball, because of negative work. But don't worry about it. Don't get tensed. It is stored safely. That is very important. It is stored safely. In which form? As gravitational potential energy, which means there will be an increase in the gravitational potential energy. Actual value is not important. The change is always what is important. By how much? 150 joules. So if the gravitational force does minus 150 joules, gravitational potential energy will increase by plus 150 joules. Think about the exact reverse scenario. When the ball is coming down, then the work done by gravity will be plus 150 joules. You will be like, how was gravity able to do work? Where did it have it? It had it in the form of gravitational potential energy. So gravitational potential energy change will be negative. It will be minus 150 joules, whereas work done will be plus 150 joules. So they will always have opposite signs, is what you should understand. Work and potential energy. Work and potential energy, they will have opposite signs but same value. Did you understand it? If any force did negative work, it has stored it in that form. If it did positive work, it has given it out. So potential energy decreased and it ended up doing work. So that's why they have opposite sign but same magnitude. Hence, I can in general say that the work done by a conservative force, okay, if work is done by the conservative force, it reduces or basically changes the potential energy. So if it is gravitational force, then there will be a change in the gravitational potential energy. If this was not gravitational, if this was spring, this will be spring. If this was electric, then this will be also electric. Basically, in general, the work done by the conservative force is minus delta U of that conservative potential energy. This is a very, very important formula, guys. A very, very important formula. Is this absolutely clear? Yep. Now, you should also remember one thing. As we are doing this, see, this ball won't go magically up. I will be pushing it, or I would have thrown it. That is the reason why it went up in the first place. So do not forget, at the same time, somebody might be pushing it or pulling it. So because of that push, which is external in nature, the ball was able to go up in the first place. I threw it, I pushed it. So whatever work I would have done is exactly plus 150 joules. So work done by external force will be plus 150 joules, which tells me every time you do work, one person does positive, other person does negative. Remember, always it goes in pairs, one positive, one negative. So the external force does work, the conservative force sucks that work, and it stores it faithfully by increasing its potential energy. While coming down, you can say delta U will be negative, gravity will do positive work, external force, if at all, that will be doing then negative work. Okay, keep that in mind. Is that clear? So the signs will change accordingly, okay, depending on the direction. So a better way of completing this will be to write down over here is also equal to, I can say, is also equal to minus, minus work done by external force, is also minus work done by external force. So this completes this particular formula. This completes this particular formula. Let me give you examples on this so that you are very, very comfortable. Say a conservative force of 3 𝐴 displaces a body slowly under external force by actually I should not use this, sorry guys, an external force of 3 𝐴 displaces slowly by 2 𝐴 meters. Question is, find number 1 work done by external force, number 2 work done by conservative force, number 3 the change in the potential energy. These are the 3 questions. Let's try to solve them. First of all, an external force of some 𝐴 displaces slowly by 2 𝐴. So let's understand why is it moving slowly. Maybe because this might be your body, this might be your external force. Because it is going slowly, slow motion means no change in the speed or very small speed. It must be balanced by an equal and opposite force. So the conservative force will be exactly opposite to the external force. That is why it is slow or negligible speed. Now let's solve these questions one by one. First, work done by external force. If you ask me, work done by external force, if you ask me, the force itself is 3, the displacement itself is 2. So basically it will be 6 joules. It will be 6 joules and it will be positive. Why? The force and the displacement are in the same direction. But if you ask me what is the work done by the conservative force, it will be negative. Think about it. Because it will be exactly opposite to it. So it will be minus 3 into 2, which means it will be minus 6 joules. That is the second part. And this always has to be true. External and conservative both will have a sign difference, just like over here in this formula. Conservative force and external force work done will have a sign difference. But what about delta U now? Now delta U is nothing but minus work done by the conservative force. That's how the formula goes. This and this, they both have opposite signs, delta U and conservative. So that's the reason why I will put minus. Work done by conservative was minus 6. Hence it will be 6 joules of the change of potential energy. That's the answer. Clear? Everybody understood the relationship between external, conservative and delta U. Three things related to each other by this equation, and believe me, this equation will also come in magnetism and electrostatics and so many other places, and every time people make a mistake. In NCERT also there is a very nice example which we have solved in the NCERT series line by line. Last lecture, I think, in electrostatics and Gauss law. Okay, great. Now that this much part is clear, we can find out how much gravitational potential energy is there, etc., with very simple ways. So gravitational potential energy, guys. Imagine somebody takes some mass and moves it somewhere like this, places it over here, places it somewhere over here. This is your initial location, this is your final location. What you know is that there is a height difference of h. This length is something like L. Okay, this is the height, this is that length. How much is the change of the gravitational potential energy? In order to find the change in the gravitational potential energy, I can say it is also negative of the work done by the gravitational force in this particular path. But remember, gravitational force is a conservative force, so work done should be independent of the path. So I will choose a very easy or convenient path. I will take it up like this and then take it up like that. So it will be minus. That work done will be work done in raising it by height h, and then work done in moving it sideways. So first I am basically taking it up, then I am taking it sideways. So that is what this would be. What is the work done by gravity in taking it up? Just if you take it up, force of gravity is down, displacement is up, so work done will be negative. So minus mg is the force, displacement is h. Minus mg is the force, displacement is h, minus sign because force and displacement are opposite to each other. Plus, when you move it sideways, gravitational force is perpendicular to this displacement. So this will not even do any work, guys. So just put a 0 over here. So minus into minus is plus, so it will be just mgh. So the change of the gravitational potential energy, simply put, is mg into h. Is that clear? Very, very simple derivation for how this mgh comes. This is the actual derivation. Anything else is just some random thing. Okay. So the gravitational energy change only depends on the gravitational potential energy change. The gravitational potential energy change depends on height difference only. On height difference only. Keep this in mind. Next, let's calculate the spring potential energy. Spring potential energy. Now you can take a spring. Right now maybe it is at its natural state, and this natural state I will call it as zero potential energy. Now what somebody does is they either compress it or extend it. So there is some kind of deformation. So it has been deformed basically. So I want to find how much is the spring potential energy. It is the negative work done by the spring force. It is negative of the work done by the spring force. When I do this, the spring applies a force in this direction. The spring applies a force in this direction. Is that right? Exactly like this. Perfect. So in calculating that work, because the spring force is itself a variable force, remember spring force magnitude wise is kx, so I will have to definitely use integral spring force dot dx from 0 to x. That is the only way, because this is variable. No issues. Let's do it and see how much do I basically get. But remember, this force and the displacement both are opposite. So that is the reason why I also need to put a minus sign, or if you are not able to agree to it, just put cos 180. Then you will see it. Just put cos 180 because displacement is here, force is here, both are opposite to each other. So that's why cos 180. Cos 180 is minus 1, minus into minus will become plus. And now the remaining part, this will be integral. Spring force is basically kx and this is dx from 0 to x. So k, x's integration is x square by 2 from 0 to x. So when you substitute the limit, you will get half kx square. That is nothing but your spring potential energy. That is nothing but your spring potential energy. But there is one more thing over here. Since we assume this as zero potential energy, so this will be nothing but final minus no extension. When there was no extension energy, that was zero, so it will just be u. So it will just give me the exact amount of the spring potential energy if I assume no extension as zero. Okay, keep that in mind. So delta means change, final minus initial. Initially it was 0, natural state. So anything minus 0 is that same number. It will come over here as it is, half kx square. Cool. That is how you calculate spring potential energy. Right. Let's do some simple questions. A block is moved as shown. Slowly. Find number 1, work done by external force. Number 2, work done by gravitational force. Number 3, delta U. Okay, so you go like this, you go like this, you go like this, and you go like this. So in this process, question is, what is the work done by external force, gravity, and change in the gravitational potential energy? Come on, my dear students, it's not that difficult. You can easily solve it. Remember, what did I just tell you? For finding the gravitational potential energy change, it only depends on the height difference, nothing else. So strictly speaking, just find what is the height difference. If you find that, it becomes very easy. See guys, you have gone down by 10, come up by 2. So technically speaking, the height difference should be 10 minus 2, which is 8 meters. You have gone down by 8 meters. So if you calculate the potential energy change, it is very simple. mgh, m is 5, g is 10, height I'll put down, so I've gone down, so it will decrease. If I go up, it will increase. So 8 5s are 40 and one more 0, so minus 400 joules should be delta U. Is that right? Next, what about the work done by the conservative force? It is negative of this change. So it is negative of negative 400, which is plus 400 joules is the work done by the conservative force. Lastly, what is the work done by the external force? It is negative of that particular work. So hence this will be minus 400 joules. This is work done by the external force in bringing it over here. Done and dusted. Clear? Shall we go ahead to the next question? Everybody? Very good. Let's move on. A spring of constant 200 Newton per meter is brought to its natural state, from an extension of 4 meters. Question is, find number 1 delta U spring energy, number 2 work done by the spring force. Okay, come on, try to figure this out. Very straightforward question. How much is the change in the spring potential energy and how much is the work done by the spring force? Slowly, why not taking friction? Shalini, that friction is counted in that external force. So in that previous thing, the reason why it was done slowly, maybe normal, tension, friction, whatever was there, all those external forces together did a negative 400 joules. Okay, because it was slowly, that is already counted in it. Okay, first of all, let's see if I get it from extended to its natural state. See, initially it will have half kx square energy. Finally, it will have 0 because it is brought to its natural state. This was it extended. So therefore, delta U, which is final minus initial, this will be 0 minus half kx square. So it will be minus half kx square. Therefore, delta U will be negative. K value is 200. Spring's extension is how much? 4 meters. So 4 square. So minus 2 cancels. 4 square is 16. So minus 1600 joules. That is your spring energy. If you ask me what is the work done by the spring force, remember it is negative of delta U. So it will be minus 1600, which will be plus 1600 joules. That's it. That is the answer. Is it clear, everyone? Alturu, not 800, 1600. I think you missed 1 and 2 or made a calculation mistake somewhere. Shall we go ahead to the next question, guys? Coming up on your screen, and here it is. If W work is done to extend a spring by some amount, how much more work is done to extend further by same amount? Okay, that is the question. Let's see if we can figure this out. So we had a spring which was at its natural state, potential energy was 0. Somebody extended it by some amount, let's say we call it x. Then somebody took that extended spring and extended it further. So the total extension will be basically 2x. In this situation number, let's say 1 versus 2. In situation 1, there will be some potential energy, which will be half kx square. In situation number 2, there will be more potential energy. Don't say half kx square again. The extension is 2x. Interesting. So there is clearly a potential energy difference. So if you see delta U, which is U2 minus U1, which will be half k x square. 2 square is basically 4. 1 square is basically 1. So it will be 3 into half k x square. 3 into half k x square. That is the difference of the spring potential energy from 1 to 2. But now that is not the end solution. The end solution is you have to give the answer in terms of W. W is the work done to extend the spring from here to here. That means if somebody brings that spring from natural to this condition, you have increased the potential energy by half kx square. So the work done will be half kx square. The work done will be half kx square. So this part over here is basically W. This part over here is basically W. So 3 times of W is that work done by the external force to extend it further. 3W should be the answer. So it's very interesting. To first stretch it, you did W work. To stretch it more further, you did thrice the work done because the spring force becomes stronger. So you need to perform better work because you apply more force later on. Got it, everyone? That is how you solve this question. So all these are questions where you calculate spring potential energy, etc. Okay. Now, there is one more extension to this particular formula and I'll just show it to you right over here. This will be used specifically in your 12th standard. So when I say conservative force is minus delta U, this equation is valid for a large or a finite change. For a finite change in potential energy. Imagine for a very small change, for a very small change, what will happen? This work will be dW. This delta will then become d, so it will become minus du. Work done is nothing but force into displacement. Perfect. Therefore, what happens is I will get our conservative force is minus du by ds. This du by ds is called as gradient of potential energy, and this negative sign comes over here. So I will put conservative force is negative gradient of potential energy. The meaning of the word gradient is derivative, but with respect to position. If I say rate of change of pressure, it means how pressure is changing with time. But if I say gradient of pressure, it means how is pressure changing with distance or position. Here it is this much, there it is this much. What is the rate of change of that quantity with respect to position? So hence that is called as gradient, which means derivative with respect to position. So again, a very, very important formula. This also has significance in a graph, meaning just imagine somebody gives me a graph of potential energy versus distance, and let's say that graph looks something like this. If I draw a tangent to this particular curve, this is y-axis, this is x-axis, this is u, this is s. So if I measure this angle, then remember this tan theta will give me du by ds. Basically just the gradient. So this gives me nothing but the gradient, not the exact force, but the gradient of the potential energy. If you draw a tangent, very, very important, the slope. So tan theta, which is nothing but the slope of potential energy graph, gives me the gradient of potential energy. By putting a minus symbol, you can get the force as well. Let's see some questions based on this so that you get a hang of it. Say for example, I tell you, listen, the potential energy is given by 3x raised to 5 joules. Find the conservative force at x equals to 1 meter. That is the question. What you will do in such situations is that go back to this formula. The force is related to the potential energy by this formula. If you know energy, you can differentiate it, put a minus sign, you get the force which is associated. So my dear students, what you need to do is just write down this. The conservative force is minus du by, instead of putting S, I will put x, because everything is in terms of x only. Everything is in terms of x, so don't worry by putting s, just put x. So 3x raised to 5's derivative. Guys, 3 will come outside. Just take the derivative of x raised to 5. What is the derivative of x raised to 5? It is 5 times x raised to 4. So what will that conservative force be? Minus sign, as it is 3 5s are 15, x raised to 4. But at 1 meter. At 1 meter, what will happen? That force at 1 meter will be minus 15 into 1 raised to 4. So it will be minus 15 Newton. That is the value of the force. That's it. It's so simple. If you are given energy, you can find the force by differentiating it. You can find the force by just differentiating it. Got it? Not 60, guys. 1 raised to 4 is 1 only. Okay? Be careful. Let's do one more question so that you guys have a hang of it. If u is equal to 3x square minus 2x plus 5 joules, where is the conservative force 0? That is the question. Where is that conservative force value? Where means the value of x? 0. So first let's find out the force in general. Let's find out the force in general. It is given by minus du by ds. Here everything is in one dimension, so I will put that x value over here. So minus derivative of this whole thing, 3x square minus 2x plus 5. So minus derivative of 3x square. X square's derivative is 2x minus 2 into derivative of x is 1. Derivative of a constant is 0. So 3 2s are basically 6. Minus into minus plus. So plus 2. So that is the value of the conservative force. Once I get this, I want to find where is it 0. So 0 is equal to minus 6x plus 2. So basically 6x is equal to 2. So x is equal to 1 by 3 meters. So the answer is at 1 by 3 meters, the force is going to be a big fat 0. Is it clear? Yes. Vaishali, very good. Awesome. Excellent. Next question coming up on your screen. This is potential energy, this is x. Okay, so the question is as follows. Find the force at x equals to 0, force at x equals to 10, where is force 0? These are the 3 questions. Okay, chalo, let's try to solve this. Find the force at x equals to 0, that means at origin, then at x equals to 10, and where is the force itself going to be 0? Let's try this out. First part, x equals to 0 means originally at the origin. So if you just draw a tangent over here, the tangent makes an angle of 45 degrees. So at x equals to 0, the slope will be, at x equals to 0, the slope will be tan of 45, which is 1. That means the force which is negative of that slope. Why is it negative of the slope? Because it is negative of du by dx, which is same as saying it is negative of, which is same as saying it is negative of that slope, which means it is minus 1 Newton. So the force at the origin is negative 1 Newton. Similarly, if you draw a tangent here, at x equals to 10 meters, the slope will be tan of 37 but with a negative sign. Why negative sign? Because it is going down. What is tan 37, guys? It is 3/4 or negative 0.75. So therefore, the force over there, which is minus du by dx, which is negative of the slope, that will be negative of minus 0.75, which means it will be 0.75 Newton. That is over there, 0.75 Newton. Lastly, where is the force 0? If force has to be 0, that means du by dx with that negative sign should be 0. That means the slope should be 0 somewhere. Where is the slope 0? Exactly over here. Exactly over here. So that means at x equals to 4 meters. At x equals to 4 meters, the slope is 0. Clear? How to solve these potential energy questions which are associated with force or with graphs? They are very, very straightforward, guys. You don't have to break your head so much. Cool? You will be able to do it if you know the formula. So what are the formulas that we have learned till now? Force is negative gradient of energy. We have also seen gravitational energy mgh, spring energy is half kx square. But in general, this is the main governing equation. Conservative force like gravity, electric, elastic will be always negative of potential energy, and this will also be negative of external work done. This is the main governing equation. Okay. Now let's come to the combination of kinetic and potential energy, which is then called as mechanical energy. So simply put, mechanical energy is nothing but the sum of kinetic and potential energy. That's all. Potential energy. So if I take potential energy and if I take kinetic energy, if I add them, what I get is the mechanical energy of the system. So if somebody wants to find the change in the mechanical energy of the system, then you have to just find how much did the kinetic energy change and how much did the potential energy change. That will give you the change in the mechanical energy of the system, simply put. So this is something which you should definitely know. E is k plus u, or delta is delta k plus delta u. Now why we are talking about something called as mechanical energy? Because there is a law called as law of conservation of mechanical energy. Law of conservation of mechanical energy. What does this law say? It says if no non-conservative force or forces do work, then the mechanical energy of the system is basically conserved. Which means all those evil forces, remember, tension, friction, etc. Friction, tension, normal, drag, or even viscous, so many other evil forces. If they do zero work, if non-conservative forces are not doing work, if no non-conservative forces do work, or basically if non-conservative forces do not work, I would say, don't perform work. Don't perform work. Then mechanical energy is conserved. That means it says, implies that mechanical energy is going to be constant. Mechanical energy is going to be constant, which means initial kinetic plus initial potential energy will be final kinetic plus final potential energy. That is what this law of conservation of mechanical energy is. Very simple. Okay. So evil forces should not be there or should not do work, then everything is fine. You can just say total energy before and total energy afterwards is the same. There is no change in that. Let's take examples of this. Let's take examples of this. Imagine there is some kind of a roller coaster which goes like this. There is a box over here of mass m. It is placed at some height over here. And this track is given to be completely smooth. This block is left and it goes down, slides down and it compresses the spring. The question is, what is the max compression? What is the max compression in the spring? In the spring. That is the question. Let's try to do this. See, in this particular problem, when the box is left, it starts accelerating. It gains a lot of momentum. It uses that momentum to compress the spring and eventually the spring gets compressed by a maximum amount. As this box slides, there is a normal force on it which is non-conservative, that should raise eyebrows. But the best part is this non-conservative force does zero work because the displacement is exactly perpendicular at every given time. So because of which I can say that mechanical energy is definitely conserved. Spring and gravity are anyways conservative, so don't bother. It's basically the evil forces that you should keep an eye out. Okay. So once we are safe to conserve mechanical energy, I will say whatever initial energy was there should be exactly equal to the total final energy. This is the initial, this is the final. I would assume now that this line to be the zero gravitational potential energy line. So as per that, originally gravity wise you have potential energy. How much potential energy you have? Think about it. You have mgh potential energy. Spring wise there is no compression, so no spring energy at all. You have just released it, so kinetic energy wise you hardly have anything, so that is zero. This completes the initial part. When maximum compression happens, the spring gets compressed, maximum compressed, and then it comes back. When that maximum compression is there, the spring has stopped moving. It has stopped elongating, compressing altogether. So there is no motion. It is at a pause for a moment. So no kinetic energy there. Did you understand why final kinetic energy is zero? Everyone? Lastly, you have come down to the ground level, zero potential energy level for gravity, but spring wise the spring is completely compressed. So spring wise it will be half kx square. So take that 2 over here, 2 mgh, bring that k down, that will be x square. This means x will be root of 2 mgh divided by k. That is the answer. Clear how to solve this problem? This is a question on energy conservation, as simple as that. There can be more questions like this. Imagine this is one of the most famous question. Mass is there, this is L, there is a hinge, this is like a pendulum. And then you release this pendulum. So eventually it becomes straight like this. It gets some velocity over here. The question will be, what is this velocity? It was released from here, it came down over here. This entire angle was theta. Question is, what is that velocity down there? Okay. It makes sense to see that, okay, when I release it, there was some gravity which was storing some energy, and when it was left, the gravitational energy got converted into kinetic energy. So to find gravitational energy stored, I will need what is the height difference, right? Without that, I can't solve the problem. So to find that height difference, I think let's draw a horizontal line maybe like this, so that it will be easy for me to figure out how much is basically this. Which is that height difference right over here. Okay, to find this h, if I know this and this, I think this whole length minus this will be the remaining length. This whole length I already know what it is. This whole thing is length L, which is the length of the string. But do I know this much length alone? I think I know that. If this is a right angle triangle, can you see that? Then only this much hypotenuse theta adjacent to it, so it will be L cos theta, this much. So this h will be nothing but that entire length minus only this much, which is L cos theta, guys. So that h will be L common 1 minus cos theta. This is useful for me to solve the problem. Okay, that is done. But I have one concern. When this pendulum is coming down, it is displacing like this. There is a problem, and the problem is there is tension. There is tension in the string. Tension is a non-conservative force. So I should be very, very alert. I should be careful. But the good part is it is perpendicular. So work done by the tension is zero. So no tension only for us. So conservative forces are only there. So hence I can say mechanical energy is conserved, is basically conserved. So whatever original kinetic and original potential is there is equal to final kinetic and final potential. As simple as that. So what is the original kinetic energy over here? It was released. So definitely it is zero. What was the gravity potential energy? Well, again I can say I will take this line as my zero gravitational potential energy line. So with respect to that, this line over here has a potential energy of mgh. Finally, it has some speed. So kinetic energy is there. But gravity wise, it came on the zero reference line. So mm cancels. So g into h. H over here is nothing but L multiplied by 1 minus cos theta is equal to v square by 2. Take that 2 on the other side. So velocity will become root of 2gl 1 minus cos theta. 2gl 1 minus cos theta. Is that clear, everyone? Understood? Clear? How to solve these mechanical energy conservation problems, right? Okay. Let's do one more question. A ball of 2 kg dropped from a height of 50 meters has a speed of 20 meters per second. When it reaches down, the work done by the drag force is how much? It's a very different kind of question, and you will see also why it is different. A ball is released from the top height is given, mass is given. Question is, if the speed is this much, how much work is done by the drag force? Why we consider zero gravitational potential energy? Always remember, potential energies are calculated with respect to some zero reference. Let me go back and show you that slide, which I showed it here. Yeah, remember this. Potential energy has no importance, it's the change which has importance. But whenever you write these values, it is with respect to some zero reference, zero configuration. So you always need to assume one point or one line as zero, and with respect to that you calculate how much is the change. So you take maybe this as zero, so this is plus mgh. If it goes down, minus mgh. So that is the reason why in that particular problem we took that line as zero. Is that okay? Even in this problem, you have taken that line as zero. So with respect to that, how much energy it has. With respect to this line, how much extra energy it has. The change is what that matters. The values don't matter. The change will automatically adjust itself. Is that clear? Sudarshan KV? Okay. Now see guys, in this problem what is different is that if you see how much is the gravitational potential energy, it will be m into g into height. 2 into 50, 100, 100 into 10 is basically 1000 joules. Which means this ball right over here, this is the ground level, it has no kinetic energy, but potential energy is there. But when it comes down, potential energy is not there, kinetic energy is there. How much kinetic energy it has? We can find that also. Kinetic energy is half into mass into velocity. How much is the velocity? 20. 2 cancels, it will become 400 joules. The funny part is these two numbers are not matching. So if somebody tries to do this, initial kinetic plus initial potential is equal to final kinetic plus final potential. Initially there was no kinetic, potential is 1000. Finally kinetic is 400, potential is 0. Clearly these numbers don't match. Which means mechanical energy is not conserved. Did you understand it? Mechanical energy is not conserved. Why did potential energy not convert into kinetic energy? The hint lies in this word, drag force. Air resistance is there. So air resistance sucked away some energy. So how much energy did it suck? We can find it out by this simple calculation. I just told you some time back, if mechanical energy changes, find the change in the delta K and delta U. That's it. That will give you the value of how much mechanical energy has been lost. Obviously from 1000 to 400, there is a loss of 1000 minus 400, which is 600 joules. Where will it lose? Where will this loss happen? Drag. So work done by the drag force will be minus 600 joules. That is the answer. Can you see that? Gravitational was more, kinetic finally was less. So there is some loss. How much was the loss? 600. So where did it go? Air resistance. But it will do negative work. So this minus sign, because work is also a sign sensitive number. Is it clear? Shall we go to power now? Do you have power left or no? Shreyas Sir is standing, but do you guys have power left or no? Ready for power? Okay, cool. Let's see. Power is nothing but the rate of doing work. Rate of doing work is just called power. So say for example, somebody climbs up the stairs and does 100 joules of work and maybe in 10 seconds. Another person also climbs the stairs, same stairs, 100 joules, but very slowly, maybe in 100 seconds. He has done 100 joules in 10 seconds. He has done 100 joules in 100 seconds. So 100 joules in 100 seconds is 1 joule per second. Here, this is 100 joules in 10 seconds. 10 seconds. So this is 10 joules per second. So this has more power. This has consumed more power. And here it is obviously less power. How quickly you use up that energy or you deliver that energy, that is called power. So that is why rate of doing work. So power will be nothing but dW by dt. But you can modify it. Work done is force dot displacement, right? So you can write this separately like this, ds by dt. What is ds by dt? It is velocity. So it is simply put force dot velocity or dw by dt, one and the same thing. So power is dw by dt or force dot velocity, one and the same thing, guys. One and the same thing. It is also a scalar quantity. It is having a unit. It is having a unit of watt. A watt is when you do a joule of work in 1 second. And there is another imperial unit which is called as horsepower. Horsepower or HP, which is nothing but 746 watts. 746 watts. Keep this in mind. So that's all that you should know about power, but we'll do some questions so that you get an idea of it. Let's do. Okay, get ready. A stone of m mass is dropped. Find the instantaneous power delivered by gravity as function of time. As function of time. Okay. How does it depend on time? That's the question. A stone is dropped from rest. So how does it depend on time? Let's solve this question. So this is our stone. This is of mass m. It has been dropped. That means the velocity was 0. After some time, obviously this particular stone will have some velocity at some time. Question is, what's the power at that moment? Well, the forces acting on it are gravitational force. Gravitational force is basically mg, and we know that power is nothing but force dot velocity. I know the force, I know the velocity, my job is done. So simply put, I will say power being force into velocity. Force is mg, velocity is v. What is the velocity then? What is this velocity? Guys, let's use kinematic equations, no? V is u plus at. Initial velocity 0. Acceleration g. So it's just going to be gt. So just put gt over here. Hence the answer will be mg square into t. That's the power. That's the answer. Job is done. Very simple question. Sometimes people unnecessarily complicate it. They give some weird answers, but actually it is very straightforward. It had the application of force dot velocity. As simple as that. Clear? Let's do next question coming up on your screen. If the power is given as 2t square, then if the kinetic energy is given as 2t square. Potential energy is given as 5t minus 2 joules. Find the power loss formula. Find the power which is lost or gained. Power which is lost or basically gained as a function of time. Let's try to solve this. Okay, kinetic energy is given, potential energy is given, and they have asked you what is the power. Now see, in this case, force is not given, kinetic and potential energies are given. So my eyes go on this formula, rate of doing work. Okay, so what happens if I add kinetic and potential energies together? I will get the total energy, which is K plus U, total mechanical energy. So it will be 2t square plus 5t minus 2 joules. Now, if I derivate this dE by dt, the rate at which energy changes, that will also be the rate at which work will be done. Therefore, the power which is gained or lost, which is dW by dt, will also be dE by dt, which means you just have to take the derivative of 2t square plus 5t minus 2. Therefore, the power will be derivative of 2t square is 2 into 2t plus 5 into 1 minus 0. So it will be 4t plus 5. 4t plus 5. That is the power which is being consumed as a function of time. As simple as that. Clear? Let's do one more question. Water is pumped at 20 kgs per second from a pond to a height of 10 meters, gaining a speed of 40 meters per second. Find the power of the pump. Find the power of that particular pump. Let's try to solve this question. These pump questions are also very, very common. Let's try to understand what it means. Just imagine in 1 second from the pond, there is a pump over here which takes that water and takes it to some height, gives it a speed of 40 meters per second. Height is 10 meters and every minute, how many? 20 kg, sorry, every second 20 kgs are going up per second. So what is that power of the pump? Obviously the pump is doing work. If you can calculate how much work it is doing per second, you have obviously calculated the power. So let's do all the calculations in 1 second. So in 1 second, what happens? The change in the potential energy, the increase in the potential energy, which is mgh, will be mass, which is 20, g, which is 10, height is also 10. This will be 2000 joules. So in 1 second, 2000 joules of gravitational potential energy is gained. Okay. Also, there is an increase in the kinetic energy, so half mv square. So mass is nothing but 20. Velocity is nothing but 40. So square it. 20 by 2 is 10. 40 square is 1600 and one more 0 over here. So 16,000 joules. So the total energy which you have gained is 16000 plus 2000, which is 18,000 joules in 1 second. All this energy you have gained from whom? The pump. So the power of that particular pump is nothing but 18,000 joules per second, which is 18 kilowatt. 18 kilowatt. So the power of the motor is 18 kilowatt. Got it? Is it absolutely clear, my dear warriors? Understood how to solve this question? Let's do one more question, guys. There was one more question like this. If power is constant, then velocity is proportional to which power of time? If the power is constant, then velocity is proportional to time raised to what? That was the question. So let's try to solve this. See, power, we know, is force into velocity. Also, force is mass into acceleration. Now we have to find how is velocity related to time. There is no time in this equation, but somehow we have to get time. So let's see what we can do. Don't say, sir, we'll use kinematic equation and I'll write V is equal to U plus AT. If you write V is U plus AT, wrong, because who said you can use kinematic equations? Like, I thought, sir, it is valid. No, it is only valid when acceleration is constant, not otherwise. So guys, what you will do is, you will take acceleration, write it as derivative of velocity with respect to time. Now shift these things. P is here, M is here, take dt on the top, and over here you have v dv. Just rewriting it slightly better, you will get v dv is equal to p by m dt, but you put the integral sign now. But you now put the integration sign. P by m v dv dt, dt dv, you can integrate both sides. P by m is constant, so bring it outside the integration. That's it, your job is done. From 0 to t and from 0 to v. That's it. So integration of velocity, v raised to 1's integration is v raised to 2 by 2 is equal to p by m is a constant, dt's integration is t. So therefore, v square is 2p by m into t. So v will be root of 2p by m t raised to half. So velocity is proportional to t raised to half. That is the answer. Clear how we solve this? So we have deliberately involved time by writing acceleration as derivative of velocity. So then I can see that integration can be done. You're like, sir, how will it click in the exam? That's the reason why I'm doing all types of models of question in these sessions, so that you have not only understood the concept, but see, if you see this slide, it feels like, ah, sir, I know power. It is so simple. dw by dt, f dot v, it's a scalar, this is the unit. But actually, when it comes to solving problems, you know, it is a complete different thing. The more you see a teacher solving questions, the more you understand. So when students tell me, sir, I'm not able to solve problems, number one, you have not seen a teacher solving problems. Number two, you have not practiced enough questions. Number three, you have not seen many solved examples and done it on your own after the class is over, or, you know, in your spare time, you just try to see what will happen if this happens, that happens. So if you try all these things, 100% you will get that confidence and slowly go from basics to, you know, advanced level. Yeah, slowly go from basics to NCERT, then PYQs, and maybe achiever section, all right, or more complex questions, or definitely you will be able to crack it. Okay, so beautiful question, guys. So we have completed this particular chapter. Okay, I hope you enjoyed the class and you are smashing that like button, and if you have not yet done that, do it right now for all the efforts that we put in for all of you. And also stay subscribed on to the Vedantu NEET English channel. Okay, bye bye, have a great time and see you in the next class. Take care.